Welcome to this online training about high-performance memory interfaces in Intel Agilex devices. My name is Steve. This training is available for desktop viewing as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. The main objective of this training is to get you familiar with the parallel external memory interface options available in Intel Agilex FPGA devices, and how to implement them in your designs. You'll learn about the architectural features available in Intel Agilex devices that implement memory interfaces. The architecture is different from previous device families, so it's important to understand the underlying architecture to see how everything works and how external memory interfaces are built. You'll then get familiar with the design flow for the memory IP for new devices called Altera EMIF FM. This includes simulation, timing analysis, and using debug tools to verify the correct operation of an interface. Here's the full agenda for this training. This third part covers the verification of an interface through simulation and timing analysis. The final part, available on the Intel FPGA training website and linked at the end of this training, will discuss on-chip debugging of a memory interface. As mentioned, when you registered for this training, it is highly recommended that you have previously watched the first online training listed here, or have experience with implementing external memory interfaces in other FPGA devices. The first online training linked here goes into detail on the basics of external memory and implementing memory interfaces in older devices that use the Unify IP and the high-performance memory controller. The second linked training discusses memory interfaces in Intel Cyclone 10, Intel Aria 10, and Intel Stratix 10 devices. It builds on the information presented in the first training. There are some similarities in the EMIF implementation between the Series 10 devices and Intel Agilex devices, but the architecture and capabilities are different enough that this training is your best resource for an Intel Agilex implementation. For more detailed information about all aspects of the memory IP and implementing a complete memory interface, see the External Memory Interfaces Support Center and the Memory IP user guides available there for each device family. It's a good idea to always have the EMIF IP user guide for your targeted device available. They are the definitive guides for every aspect of creating a memory interface using an Intel FPGA and will be referenced throughout the training. Once again, here's the recommended design flow for creating a working EMIF interface. In this section of the training, we'll look at how to perform a functional simulation of the interface. A simulation is completely optional, but it is recommended to verify that your parameterized design will function correctly. Once you've added the Altera EMIF FM IP to your design, you can perform a functional simulation to verify that the parameter settings you've specified will work correctly when the design is implemented in hardware. If you are familiar with simulating memory interfaces in previous device families, the first thing to note when comparing the simulation process between the old Unify IP and Altera EMIF FM in Intel Agilex devices is that with the new IP, the synthesis and simulation file sets are mostly identical. Besides making it easier to manage the files, using the same files for both synthesis and simulation can help guarantee that simulation results will match the real-world operation of the synthesized design. The main exception to having identical file sets for synthesis and simulation is if VHDL is selected as the output HDL. In the simulation file set for VHDL, only the top-level file is guaranteed to be written in VHDL. Submodules may be written in VHDL or they may be written in either encrypted or plain text Verilog or system Verilog. As such, your simulation tool must have mixed language support, and you must follow mixed language simulation guidelines for file compilation. The ModelSim Intel FPGA edition includes mixed language support, so the example design can be simulated directly in this tool that's included with the Intel Quartus Prime software. There are also fewer files needed for simulation. Some simulation tools, including the ModelSim Intel FPGA edition, have an upper limit on the number of files that can be part of a simulation. Besides fewer files in the simulation file set, fewer of those files are unencrypted. Only unencrypted files count towards the file limit of simulation tools, so having fewer unencrypted files helps guarantee that the limit will not be hit. As with other IP, the IP parameter editor and platform designer can generate simulation models for the interface that you can use in your own simulation design. Just choose to generate the simulation model in the Generate HDL dialog box when generating the IP or system design. However, if you choose to generate the simulation example design using the option discussed earlier and shown here, a complete simulation-optimized system design is created. As with previous device families, if you disable these options on the Example Design tab, you can still run a script named makesimdesign.tcl to create or recreate the simulation files later. The simulation example design matches the synthesis example design, but includes a BFM for clock control, a generic external memory simulation model, and a simulation checker component to indicate if the simulation passes or fails. You can view the simulation system design by opening the generated edsim.qsys file in Platform Designer. If you'd like, you can replace the generic memory model with a model obtained from a memory vendor. Memory vendor simulation models can provide additional information that can help debug the controller parameterization if necessary. Be sure to follow the vendor's instructions for configuring and using the model. Note that if you regenerate the example design, the generic model will again be used. Also note that the EMIF IP does not work with the option to generate a test bench system from the IP parameter editor or Platform Designer Generate menu. Create the simulation example design instead. When creating the synthesis or simulation example design, you can replace the default traffic generator with the new version 2.0 of the IP, referred to as TG2. This new traffic generator block provides extensive user-configured customization of the traffic patterns used to test the external memory interface. It can also generate a basic default pattern similar to the original traffic generator, with single and block writes and reads to sequential and random address locations. We'll look at TG2 in detail in the on-chip debugging section of the training, but if you want to include it in the simulation example design, enable its use on the Diagnostics tab of the EMIF IP parameters as shown here. Note that currently, simulation is only supported with TG2 with the default traffic pattern, so the bypass the default traffic pattern option must be disabled. Simulation of custom traffic patterns will be supported in a future version of the Intel Quartus Prime software. To learn more about TG2, see the EMIF on-chip debugging tools training and the EMIF IP user guide, both linked at the end of this training. The example simulation system design named edsim.qsys looks like this. Much like the synthesizable example design, the simulation design has the memory interface connected to the calibration IP, the traffic generator, and reset control logic. The main difference in the simulation design is the addition of clock and, in some designs, reset bus functional models, or BFMs, and a generic simulation model for the external memory. The simulation design also includes a simulation checker block to automatically check if the simulation passed or failed. The synthesizable example design only has exported pass-fail signals that must be monitored for the results. As with previous memory IP, you can choose in the parameter editor on the Diagnostics tab whether to skip memory calibration during a simulation or to simulate the full calibration process. In most cases, skipping calibration is recommended, and it is the default option. The expected read data arrival times used for the simulation will be based on the latency values that are specified in the parameter editor. Skipping calibration can greatly speed up simulation time, allowing you to focus simulation efforts on the overall system design instead of a detailed analysis of the interface's operation. If the full calibration option is selected, the entire calibration algorithm is simulated, which can take many hours or even days to complete. A .hex file storing the calibration code gets compiled with the rest of the simulation files. Simulating with full calibration can help debugging of the memory interface itself to make sure it is getting calibrated as intended. With the EMIF IP, you can only perform an RTL or functional simulation. An RTL simulation will verify the basic functionality of the interface without taking gate-level delays into account. Gate-level simulation of the EMIF IP is not supported. It is recommended instead to perform an RTL simulation for functional verification and use timing analysis, discussed later, to verify that the interface meets gate-level timing requirements. When simulation is performed on one or more memory interfaces, a few assumptions are made. First, there is no modeling of board trace delays, since this is external to the FPGA. Next, if you are simulating multiple interfaces that have been placed in the same row at the top or bottom of the device, the simulation operates as if the interfaces are placed in their own separate rows, each with their own unique I/O SSM blocks. Calibration happens in parallel between the multiple interfaces, but the simulation does not continue until all interfaces are calibrated. However, when running in hardware, recall that each row has only a single I/O SSM block shared between all the interfaces in the row, even when they are sharing sub-bank resources, so calibration happens sequentially from one interface to the next. Each interface goes into normal operation once its calibration is complete. So with multiple interfaces in the same row, an RTL simulation would make it look like the interfaces are completely unaware of each other and calibrated in parallel. Identical interfaces would actually finish calibration simultaneously in the simulation, but would still need to wait for other interfaces to finish. Obviously, this is not an accurate representation of how the interfaces really operate. With a single I/O SSM block for each row, sequential calibration of the interfaces is required, but the order in which these calibrations are performed is not defined. Thus, the simulation results may not match the synthesis results. If possible, avoid performing full calibration simulations for multiple interfaces in the same row. With that in mind, here are the basic steps for performing a simulation on an external memory interface. First, from your existing design, generate the simulation example design, choosing either to skip interface calibration or to simulate the full calibration process. If you want to use TG2 instead of the original traffic generator to drive traffic on the interface for the simulation, remember to disable the option to bypass the default traffic pattern, as discussed earlier. Next, look for the simulation files generated for the example design. By default, you'll find them in a sim directory in a folder with the name you selected when generating the example design. Look for the folder of your preferred simulation tool vendor. A simulation script for your preferred tool can be found in this location. Now, point your simulation tool to this location and run the script found there. For example, if you are using the included ModelSim Intel FPGA Edition simulation tool, specify the simulation directory in the tool to be the generated mentor directory. In that location, run the msimsetup.tcl script, either from a command line or the ModelSim transcript window, as shown here. To learn more about the details of setting up and running the simulation, see the EMIF IP and EMIF design example user guides linked at the end of this training. Next, let's take a look at how a timing analysis is performed on an interface. Once again, here is the recommended EMIF design flow. Perform a timing analysis as early as you can in the flow to make sure your parameter settings and the board design will meet all functional, timing, and signal integrity requirements. If you have performed a timing analysis with any of the older memory IP, the flow for the latest devices is very similar. The IP parameter editor or platform designer automatically generates all the files required for a timing analysis, including all required timing constraints in a .sdc file and several TCL scripts. Executing the report DDR task in the timing analyzer automatically runs the appropriate scripts and generates timing reports. In this section, we'll take a look at the paths that get analyzed when a timing analysis is performed and look at some optimizations you can enable to help close timing. First, here's a quick review of what components in an interface make up a timing analysis. Once the interface has been calibrated, a static timing analysis can be performed on the entire design. When performing a timing analysis, it is important to understand the different components that make up the analysis. The main components are listed here. The source synchronous timing paths are all the paths where clock and data are transmitted together. The main source synchronous paths would be the write data path from the FPGA to the external memory and the read data path from the memory back to the FPGA. These are calibrated by the I/O SSM block to line up the clock or strobe with the data by adjusting clock phases. Calibrated timing paths are other paths and settings that are adjusted during calibration. These include, for example, FIFO lengths on the read data path and the adjustment of delays in the I/O for clock, strobes, and data deskew. Internal timing paths are all the other internal paths that make up the memory interface. Finally, the FPGA timing parameters are all the settings applied to the design, such as termination and drive strength, as well as specifications that are inherent to the chip itself, such as device speed grade and jitter. Here is a diagram of the timing paths and areas analyzed in Intel Agilex devices that use Altera EMIF FM. For timing analysis, the interface is divided up into three parts: the core, the periphery, and the I/O. The core includes all paths and logic outside of the controller and PHY. If a soft logic requiring feature was enabled, such as ECC, that logic is also included in the core analysis. Recall that the EMIF IP provides constrained clocks to drive your custom logic and any other soft logic in the core. The periphery includes the controller and PHY, extending to the I/O registers, and the I/O includes all the paths to and from the external memory. A core timing analysis looks at fewer areas than previous device families because most of the logic is hardened. Timing on most of these paths was met when the device was designed. With the user logic running in quarter rate or half rate modes, the core analysis includes the core to periphery and periphery to core paths, referred to as C2P and P2C. If ECC has been enabled, that logic is also included. The user logic that issues read or write commands to the controller, such as your own custom logic or one of the traffic generator blocks, is never included in an EMIF core timing analysis. This logic, as always, needs to be constrained and analyzed on its own. Again, it is recommended that the constrained output clock from the CPA in the hardened interface, EMIF user clock, be used as the main clock for the user logic. In previous device families, periphery timing analysis was included with the core analysis. However, with Altera EMIF FM, periphery timing analysis is not necessary and not performed. The timing of the hard controller and PHY has been closed at the factory. You will not see periphery-to-periphery analysis in the timing reports, as you would have seen in previous devices. The only periphery analysis that is performed is a minimum pulse width check. This makes sure that the interface is not set up to run faster than the device can handle. Other than this, no periphery analysis is performed. When the IP is generated, several timing-related files are created and stored with the main design files in the synth directory shown. The main.sdc file is pointed to by the .qip file. It is not necessary to manually add this file to a project. The ipParameters.tcl script lists a number of parameters that were set when the IP was configured in the parameter editor. These parameters are used by the .sdc file and other scripts. The parameters.tcl script provides device-specific parameters. The pinmap.tcl script includes helper functions used by the other scripts. The reportTiming.tcl script is the main script run for a timing analysis. It is the script called when the report DDR task is executed in the timing analyzer. The reportTimingCore.tcl script contains the main timing analysis algorithm used by report timing. When the report DDR task is executed in the timing analyzer, the reports generated are very easy to read and understand. A simple spreadsheet-like summary report is generated for each timing model, and more detailed path reports are generated for the core, P2C, and C2P analysis. An example of one of the summary reports is shown here. In previous devices, it was sometimes difficult to meet core timing due to excessive delays in the C2P and P2C paths. With Intel Agilex devices, the hardened IP allows for much shorter paths between the core and the periphery, reducing delay as much as possible. Also, using the CPA-generated clock for the core and user logic helps reduce or eliminate clock skew between the core and periphery. If you are having issues meeting core timing, check that the CPA clock is being used correctly, and check related timing parameters in the parameter editor. Verify that the .sdc files generated by the IP are listed in the project's timing analyzer settings. If necessary, you may need to enable optimization settings to help close timing in the core. Try adjusting the synthesis and place and route optimization settings listed. See the Intel FPGA training website to find training about other basic techniques for closing timing. This concludes part 3 of the training. If you'd like to continue the training or see parts 1 or 2, you can register for parts 1, 2, and 4 for free at the links shown here. To learn about additional resources available to help you in implementing an external memory interface, continue to the next slide. There are many resources available to help you with memory interfaces in Intel Agilex devices. The documentation resources listed and linked here should be the first ones you visit. The EMIF Support Center and the EMIF IP User Guide are your one-stop shop for all things EMIF related. Besides documentation, there are many training classes available from Intel FPGA on memory interfaces, Platform Designer, and Interface Planner. The Platform Designer classes listed here will show you how to incorporate a memory interface into a complete system design. The Interface Planner online training goes through the basics of what the tool is and how it works, along with a demonstration of its use in the placement of an external memory interface. Intel FPGA provides many additional technical support resources besides technical training. check out the online Intel FPGA forums. They're a great place to connect with other users to share experiences and find solutions to common issues. Visit the Intel FPGA Wiki for design examples and up-to-date articles written by field application engineers. Use the knowledge base to find solutions to the most common issues you may run into. Manage your software licenses and online training registrations using the Self-Service Licensing Center. Finally, for local assistance, contact your local Intel FPGA sales office to speak with a field applications engineer. One more thing. When you registered for this online training, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this training on high-performance memory interfaces in Intel Agilex devices.